in great detail, but not enough detail yet, is this idea of the E2, this idea of a bimolecular elimination process in which a base, a reactive species, goes after a substrate and takes off a proton and elimination ensues. You've got to keep these things organized. Why did the SN2 go quickly? Why did the SN2, why was it a good reaction where we didn't get SN1? It's because the nucleophile is reactive and it wants to go after the substrate. The same criterion applies here. The base here is reactive and it goes after the substrate. It does not give the substrate enough time to do anything else like give a carbocation. So we dealt with that a couple of slides back when we looked at some of these examples. There is a transition from pure SN2, where that's the major product when you have a primary system, and we get through to the secondary systems, which are quite complicated because you can get SN2 and E2. SN2 typically gives you one product. It's stereospecific, it gives you inversion, but the E2 now gives you multiple products because you can get cis and trans, you can get regioisomers. We talked about Zatev's rule, in which you'll get more of. More of that to come. And then when you get down to the tertiary systems, they really can't do much else than E2. The tertiary systems now, you're not going to allow for an SN1 here because the base is too reactive. You should be now know that that's a reactive species. That will not sit around waiting for anything else to happen. It will go after the substrate. Why can't this do an SN2? Because it's tertiary, it's too crowded. Okay, we don't have access to that electrophile. So we do an E2 instead, and you'll see now this transition and things have just got very complicated because now we're mixing everything up, which is what happens in reality in the organic lab. So with that in mind, let's talk about some of the fine details of this reaction, and then we'll get into the E1. Go ahead. Yes, I mean, that's absolutely right. I mean, the reason that the tertiary system can't do an SN2 and it goes the E2 pathway is because the SN2 pathway is too high. Yeah, absolutely defined by that. Now, there's a lot more to come in terms of energetics. By Friday, when I want to get through 8, you'll know an awful lot about equilibrium, about reversibility or lack of it, and we'll be into the real sort of detail of what's happening here. So to get started here, we talked about stereospecificity in the SN2 reaction. All that means is if you start out with the wedge isomer, you end up with the dash isomer, right? In the SN2 reaction, you get an inversion process. That's stereospecific. And what that really means is the nature of the starting material dictates the nature of the outcome. If you start with the R, typically you get the S, or the other way around. But you certainly get an inversion where one is switched for the other. And you don't get mixtures. So we're not talking about selectivity here. We're talking about specificity in which you just get one outcome. That also applies to the E2 process. Now we're talking about these guys not necessarily behaving as nucleophiles, but behaving as bases, typically in a secondary or tertiary system where it's too crowded and the SN2 can't work too well. And we'll talk now about the requirement of the substrate, how it lines up in a Newman sense, talk about sort of Newman depictions and think about all that stuff from earlier, and why that only gives us one product. Because we could argue here that we can get cis and trans. I could argue maybe that this T-butyl group could go up here, and that might be the cis isomer, where in this molecule we have the trans isomer. And you only get the one. And we've got to be careful here. It's not simply because that product is more stable, it's because the transition state getting to it is lower energy and more stable. And we'll have to build some Newman depictions to prove this, and it relies upon an ideal orientation for your beta hydrogen and your leaving group. They have to be pointing in opposite directions. They have to be anti to each other. Right? The fastest eliminations that you will see will be when the hydrogen coming off and the leaving group taking off are anti to each other. If they're syn, it might work, but it'll be slower. I'll show you why in a second. But typically now, anti-eliminations are what we're looking for. So we can see this at the bottom. Your system needs to be set up like this. Obviously, in a system here, you have free rotation. So we'll worry about, okay, does a molecule look like this, where it's eclipsed, or this, where it's anti? Anti will prevail. And we'll say now that some systems will go faster than others because of this alignment being possible. In other systems, it's maybe not possible. So think about the possibilities here. Look at the orientation of this phenyl group, this big benzene ring, and this T-butyl group. What's the alignment there, if one's a wedge and one's a dash? They look like they're anti, right? Now, is that good or bad in that system? Absolutely. The big groups are as far away as possible from each other. And here we can see that the H and the Br will line up anti, and the big groups are out of each other's way. That's a low-energy system, yes, compared to other systems. So when this happens, most of the molecules are going to look like this, where we have the alignment anti, and we'll get a very fast elimination there. So here the base comes in, we go after that proton, we dump electrons into the pi bond, and the leaving group breaks off. That's a great E2 process. Okay? So the word now is anti, and you want everything in the same plane. So the next slide describes something called anti-coplanar and syn-coplanar. If you understand Newman depictions, there's nothing tricky here. In the same molecule, you have the option or the possibility of rotation because it's not a cycle. It's an acycle, so it can rotate quite easily. In most of those molecules, thinking about populations from the Newman depiction material, most of those molecules are going to look like this anyway because all the big groups are away from each other. If I asked you that from a chapter 4 perspective, most of you who are still here could answer that properly. You'd tell me that that was the best outcome. Well, you can rotate around that central carbon-carbon bond, this one. And that will give you an opportunity for these guys to be syn coplanar. And you'll see why the anti and the coplanar idea is important in a second when we make the pi bond. Tell me about this. Good or bad? Bad, right? So the point is, very few, if any of those molecules will look like that. There is a reason why the bonds have to be coplanar, because we'll make a pi bond in a second in which the p orbitals have to be pointing in the same direction. But now we can say that the vast majority, if not all of these molecules, look like the left. Very few, if any, look like the right. So the fast elimination is going to happen from the one on the left. If you turn these things around in space, you can see why we did chapter 5 when we did the stereochemistry stuff. You now have some idea of how to manipulate these things in your head to be able to look at molecules from different angles. So you can see now at the bottom, all we've done here is turn this into this. You see why we ask you to turn wedge dashes into Newmans and Newmans into Fishers, so that you can get used to this stuff and you can practice it and get good at it. Because now we have the sort of best look at this, where the Newman depiction shows you the relationship between the H at the front and the Br at the back. They are certainly anti to each other. Now, why on earth should it be necessary to be anti or coplanar? Well, you think about the orientation to where we're going. You think about a pi bond. What direction must the p orbitals be pointing in to make a pi bond? The same. They must be pointing in the same direction. So in the molecule on the left, where I have the anti-coplanar idea, they're already kind of pointing in the same direction. In other words, the bond here, which will become part of the pi bond, and the bond at the back, which will break off, those orbitals are already parallel. Okay? The key word there is parallel. If the bonds in your precursor, your single bonds that are going to go and become pi bonds, if they are parallel, that will be a fast elimination because you don't need to twist anything. If your bonds are twisted like this, you have to get them lined up to become a pi bond. What does that cost you? What does rotation cost you? Energy. What does energy cost you in terms of transition state? Higher or lower? Higher, right? So if everything's already pre-organized and pre-aligned, all they have to do is that. Slide into place like that and overlap to make a pi bond. If they're pointing in wrong directions like this, extra work is needed to be able to do that. Ashley. The big ones, the big ones. And coincidentally, in this example, they all line up nicely. That's why we start with this. Yeah? So ideally, when you're doing homework, Chapter 8 homework is out there, Chapter 8 quiz is out there now, and we have a sit-down quiz in class next week to start getting ready for the next exam. Even though it's a month off, it's a big exam. Look at where the protons are. First of all, we learned earlier on to identify beta hydrogens. That's the first thing you look for in an elimination reaction. Now you have to identify their orientation. It's not enough that one is there, but now you'll have a choice of where to take that proton off from, and some are better than others based on this idea. You want them to be anti-coplanar if possible. So part of the problem here, if you look at the Newman depiction for this orientation, is this right here. Yeah? You'd have to say from your experience that that isn't good. So very few, if any, of those molecules look like that, and we're not going to get much elimination like that. You can get syn coplanar elimination, but this one on the left is much faster. Okay? Everything's lined up nicely, and it'll give you a pi bond very quickly. So once we've done that, we can start thinking about this idea of stereospecificity. The relationship between the starter material and the product is defined in the sense that whatever you start out with gives you a certain product, like in the SN2 reaction. Stereospecificity, the nature of the starter material dictates the nature of the product. Well, if you look at this example here, you've got a proton and a bromine. You've got the beta hydrogen and the leaving group, and they are anti to each other. And if you think about the mechanism here, it's an E2. So is it stepwise or concerted? Concerted. The 2 tells you it's concerted, so everything's happening at once. Let me say this carefully. This base is going after that proton, and at the same time, that bond is breaking and the pi bond is forming, and at the same time, that Br is breaking off. It's important you get this. Once you start making this pi bond, once you start this process, do you think there's any possibility of rotation around that central bond? No, you are starting to make a pi bond. Think about what the transition state looked like on Monday. You are starting to give this molecule some rigidity because the carbons involved to make the pi bond are going from sp3 to sp2. They're becoming rigid and pi bonds can't rotate. So as you're going up this barrier to this transition state, you're starting to get some sort of prediction for where the R groups will go. Now look at this. The red R1s here are wedges. They're on the same side. If they're getting trapped in this shape in the transition state and they can't rotate anywhere, they'll be on the same side in the product. You see that? If the blue R2 groups, which are both dashes in this case, are getting trapped in that transition state, then we're going to end up with the R2 groups on the same side. So that's what stereospecificity means. The nature of this system here in which both the R groups with the blue R groups are wedges or dashes, and the other two are wedges. They're going to end up on the same side, trapped like that. Now, it's tricky to get your head around. There's a lot of this to come up now. The stereochemical outcome will tell you what happened in the reaction. This is part of the reason we know it's an E2 process, because the stereochemistry is fixed from the starting material all the way through to the product. Down at the bottom, we can see here a different situation. R2 now, the blue pieces, whatever they may be, are in opposite directions. And the red pieces are also in opposite directions. If this really is a stereospecific concerted process, when this goes after that proton and we boot out the bromine, those R groups are stuck in the orientation they were in the starter material. That's all you need to worry about there. So in this case, the R1s end up across from each other, and the R2s end up across from each other. And you don't get the other isomers. So this is now said like the SN2, where you went from R to S, or you went through an inversion process. This is a very similar idea and said to be stereospecific. This is something you need to think about, and you start asking questions so that we understand it properly. So stereospecificity, basically you end up with one product. Well, there will be many instances in which you don't just have one hydrogen, one beta hydrogen. You might have several to choose from. And now we get something called stereoselectivity. And in this past week, we've introduced an awful lot of different terms to do with selectivity. Regioselectivity. Now we're talking about stereoselectivity, and later we'll talk about chemoselectivity. These are all the important ideas that you need to think about for biochem later, maybe. What has changed here? You have a system in which you have two beta hydrogens on the same carbon. So either this one can come off, or this one can come off. And both of them potentially can be anti-coplanar with that bromine. So depending upon which orientation eliminates, you're going to end up with two products. If you look at this system, in this case, the R1 and the R3 are pointing in opposite directions. If one hydrogen comes off, we're going to get this isomer. But if you rotate around and bring this guy up to here, you'll change the orientation of this versus the rest of the molecule. That's where this isomer comes from. So it's dependent now. What is different? The orientation of this can be several different orientations. You have two protons that can come off, and depending upon which one comes off, you get two products. In the first example, just one H came off, you got one product, now you've got two. So this isn't specificity, because you're getting more than one product. And as we work on to this idea of major and minor, that's exactly what this is, selectivity. If you get major, you're more selective for one product. So now we have to worry about real examples, and we have to start thinking about how to put this stuff together. If you want to spend some time on this today, understand the difference between those two ideas. We're about to get into a lot of reactions in Chapter 9 in which the stereochemical outcome of the reaction tells you what happened during that reaction. And that's key for getting through this class, right? All of you who are staying in the class are going to get a grade of some nature. Hopefully it's the one you want, but that's based on how much effort you want to put in and how much you understand this stuff. You must be good at stereochemistry to get through the first semester. So this little bit at the bottom is just trying to show you the difference between those two ideas. Stereoselective means you get one of more than the other, based on some reason, orientation, stability, whatever. On the right-hand side, stereospecificity means you start with this and you can only get one isomer, just like the SN2 reaction. So know the differences there. On my final exam, 37 pages, comprehensive, I'll ask you those definitions. So you must know those definitions, and I'll typically ask you to give me an example of each of those words so that they sink in and you know them for the future. Right, I'm wrapping up the E2 because I want to be in the E1. E2 is very useful, E1's a bit more confusing. What about cycles? You can do elimination reactions in cycles. You'll see many of these doing practice exams, doing practice homework, stuff like that. Well, again, some knowledge of where we were in the past with the orientation of these things, be they axial or equatorial, we now have to think about the possibility of elimination there. Because if I'm looking at a cycle, I can have my chlorine axial, or I can have my chlorine equatorial, which is actually more stable. Chlorine equatorial, right? But these groups are not that big, especially on a simple cycle like this, that they can't interconvert. You will be going backwards and forwards, which is the whole point of this equilibrium system here. It turns out now, for the same reason I did, I don't know if you got this, but your starting orbitals, the single bonds that become the pi bond, have to be pointing parallel. So they just slide in like that, and there's your pi bond. Okay? That's how it comes together, like that. That's the fastest process. Well, that's possible if you have your chlorine axial. Yes, not all those molecules will look like that, but some will, and they will go faster than the ones that don't. On the right-hand side, what's the relationship between this chlorine and this hydrogen at the back? Gauche. Good. We have this language now. We can use it quickly to talk about detail. If it's gauche, what has to happen for this system to eliminate to give a pi bond? You have to rotate. What does that cost you? Energy. Does that make it faster or slower? Slower. That's all there is to this. So this reaction on the left is faster. The one on the right is slower because the one on the left has the proper orientation for this pi bond to form. The one on the right does not. That's all there is to it. So we exemplify this by this example, this system here. Classic problem. You see this on MCATs, PCATs, whatever. You have two isomeric cyclohexane systems. Again, this could have been a question from chapter 4. Obviously, we know that stuff now. Think about exam 3, think about the final. We can put all this stuff together. On the left, I have a bromine axial, and I have a T-butyl group equatorial. What do you remember about T-butyl group? They want to be equatorial, and everything else can just go where it's told to go, right? T-butyl group is huge, so it wins, and it goes equatorial. So this molecule, is it cis or trans? Is that the cis or the trans isomer? It's the cis isomer, isn't it? Okay, they're both pointing up above the cycle, therefore that's a cis isomer. The cis isomer here may not be the most stable isomer, but it eliminates the faster of the two systems. This is the isomer now where this is pointing down, this is pointing up, they're trans. And so now if we eliminate from here, we have that problem. We have the gauche orientation of those two pieces, and they'd much rather be coplanar. They're not in that cycle. So the reaction over here is slower for the same reason as above, the fact that these pieces are pointing in the wrong direction. On the left, what's the relationship between this H and this Br? Give me some words. Anti, and what have we learnt today? Anti-coplanar. They're lined up perfectly for this to happen, and so this goes 500 times faster. If you're an engineer, that's a big number. If you're a biologist, that's a huge number. Right? You've got to get into these sort of little details now where these little numbers tell you an awful lot. When you get into things like kinetic isotope effects in biochem, tiny differences make the difference in being able to understand what's going on or not. Any comments, Jacob? Are you okay? Yeah? Just sort of hanging out. Haldeman? Anything? I got nothing. Yeah. Anybody? You will spend time over this, you'll scratch your heads, and you'll hopefully ask some questions, and you'll understand what's going on. So the E2 things have to be coplanar. How do you do this? Well, you read the textbook. The textbook is quite good on this material. You're thinking about how to line these pieces up so that you get the elimination in the correct orientation. If you were to look at this molecule as an example, it's acyclic, it can rotate, but some conformations will be preferred over others depending upon the orientation of different groups. This is the same molecule down here to finish up. So this is just solving the problem. If you were to do an elimination on this molecule with a small base, and I'll be careful here to say small base because when we use a big base, it'll be different. You're looking down here, there's an eye, looking down that axis. And you can see that the front right is the bromine. And then over here, if you look at this properly, it turns out that the methyl group is pointing anti to it. So that's not going to eliminate very quickly because these two things are pointing in the wrong direction. However, if you rotate this molecule slightly, and this is simple Newman depiction stuff, all you're doing here is grabbing this and rotating over here so that H becomes coplanar. Now you can get elimination. That's the key. If you can have an anti-coplanar relationship, you'll get a fast elimination. But what that also does is traps the other groups in space. It traps everything else in space. If I drag this hydrogen down over here, everything else has to move with it. So those ethyls and methyls, they get twisted as well. They get moved as well. What I'll have now is an orientation, if my base comes in and grabs this, in which all these other pieces are going to be stuck in space relative to each other. So can you see that the methyl groups are pointing in opposite directions in that orientation? That's why we get the methyl groups trans in the product. And the hydrogen and the ethyl group are pointing in opposite directions. That's why they're in opposite directions on the molecule there. If you get that, great. That's all there is to it. You're trapping it in the transition state, and then we're getting the fastest elimination possible, and the outcome is based on where groups are relative to each other in that transition state. So having said that, your job, next exam's a month off. It's the week before Thanksgiving, always is. Next quiz is online, the Chapter 8 stuff. Sit-down quiz next week where you've got to draw these things out. Get on this stuff as soon as you can. So here's the solution to the problem. If you were to put this thing together, as you might see next week, that's a small base. So small bases can get places. In this example, I have a hydrogen here, and it happens to be a wedge. That's not the correct orientation for this to go faster. It needs to be pointing the opposite direction, so some rotation is necessary. But what you'll end up with is more of this and less of this. We're now very much into this major-minor idea where you have to tell me about how much of each you get relative. The methyl groups up here, we're on the opposite side of the backbone. That's why this is here and this is here. The hydrogen and the ethyl group are on opposite sides. That's where this comes from and where this comes from, which is this guy over here. Where does this come from? It comes from the other side, right? We've got a hydrogen over here in which the base can go after that, and we get less of it. Now again, why? It turns out we have more of those hydrogens. We only have one of these little hydrogens in the middle, but the answer now is transition state stability. You want to have more alkyl groups on your double bond as it's developing, because they help stabilize that double bond. So we'll now see that this is the major. Any ideas why? More highly substituted, right? This is the Zaitsev product. The one on the right is the Hofmann product. It's less highly substituted and therefore less stable in the transition state as well as in the product. So we'll start talking about kinetics and thermodynamics again. We'll start talking about how fast things happen, how fast I can talk, and we'll start talking about really, really complicated stuff. Ashley. Go on, try again. Try again, I couldn't hear. They have to go with it. We spent all that time doing Newman depictions. You move this, this comes as well. Either, right? I mean, it's going to go wherever it needs to because it's the next thing along. If this was a wedge and you bring it up here, maybe this is a wedge, right? So we have some detail now, and we can start doing E2s for real. We can start thinking about why this is important, and we can start using it. And a big thing from now on is synthesis, culminating with chapter 12, which is all about putting this stuff together. There's no new chemistry in 12, it's just using everything we did to build molecules, to design and build molecules. So now we've got some ideas about the size of the base, about the reactivity of the base, and about the substrate, whether it's primary, secondary, or tertiary. What type of substrate? Tertiary. Can it do SN2? No, because once you see this and you see O- localized, you're thinking SN2 or E2. You're thinking strong reactive species. That's not going to allow for carbocation to happen. Something else will happen instead. But this is a large base, and I have to worry about, okay, there's a hydrogen here can come off, because that's in the beta position if you like, and there's a hydrogen here that can come off. Which do you think is faster, left or right, with that particular base? Yeah, I wish I had those clickers. This would be great. Okay, there's your major. That's a very large base. That will give the Hofmann outcome. That's going to have a much easier time getting to the hydrogen here, which is a primary type, than getting to the hydrogen here, which is secondary and surrounded by stuff. Fairly logical when you see it. But you have to put the time in to be able to see this. So now we've got major and minor. We can design our outcome depending upon the substrates we use and the bases that we use. I think by now you should understand this is a powerful base and it's very big. OCH3- is a very powerful base, but it's small. You should have those with you to be able to do these experiments. Problem here is going to be a little bit confused because I have hydrogens here, one of which is a wedge, one of which is a dash, and one of which could be anti, and I also have a hydrogen here, and it happens to be a wedge. Now, what's the relationship between that hydrogen and the leaving group? They're anticoplanar, right? So if you think about this as a small base, it doesn't really worry about where it's going to go, you expect that outcome, in which you get the Zaitsev product because you had everything set up to do so. You get the more stable product, not because it's more stable, but because it was the faster reaction to get there. So it's a kinetic type outcome. On the right-hand side, this is where this proton came off. There are two of them, but it's the orientation that matters, and it's also the stability of the transition state. When you've got more alkyl groups in the transition state, it's a lower energy. So now we can see how this comes together. Down at the bottom, be careful with this one. It could do two things. It can do SN1 and it can do E2. Sorry, it can do SN2 and it can do E2. Good leaving group, good base / nucleophile. It can attack there and it might give you some SN2. But if you go back and do some reading, it's not as obvious as that. What effect do you think this cycle will have on the SN2? All this stuff here, do you think it'll slow it down or speed it up? Slow it down, it gets in the way. It's crowding in the beta position. But I have one hydrogen here that can come off. So even though that's a small base, this is a crowded system. We did cover that a while back. And you should expect to get that. Okay? That's the elimination process. Confused? Probably. That's up to you to get, what's the word? Deconfused? Unconfused? To get cleverer? I don't know what the word is. But between now and next week, you need to have this stuff organized because chapter 9 is my favorite. It's huge. Good enough? So I think I'm done with the E2. E2, very useful because you can design where you want to put your alkenes. E1, less useful because you get thermodynamic outcomes. And this is a major change in something that you should be comfortable with, but often you aren't. pH. Not pKa, but pH. If I were to ask you here, what is the pH of this mixture if you measured it? Would it be less than 7 or greater than 7? Greater than 7, right? And part of the reason people don't do well in this class is that they have to think about that. You shouldn't have to think about stuff like that at this stage of your chemical lives. The pH here is basic. It's greater than 7 because we're dealing with O-. O- reminds you of hydroxide. Hydroxide is basic. You know that. 2 plus 2 equals 7. Away we go. So we change things now. In this system, as it looks on the slide right there, this looks like it's neutral. But most of what we will do for E1s is acidic. That's going to be how to tell the difference. If you have an acid, typically here it will be an E1. And that will allow you to do things like leaving groups breaking off. So what we did for the E2 was we suggested, okay, several ways of getting to the alkene involve a concerted process in which the base comes in, grabs the proton, the leaving group breaks off, everything happening at once, analogous to the SN2. The E1, what does it remind you of? We have a carbocation getting formed. What does it remind you of? The SN1, right? The SN1. So you can't use strong bases here because they'll do other reactions. They might do an E2 instead. So this is going to change quite dramatically, and it's also the beginning of hopefully you picking up. The first thing you look at is what's the pH? Not a number, but just is it acidic or is it basic? Because guess what? I said this in recitation this week. I'll do it again this afternoon. If your reaction is basic, all your intermediate species on carbon typically will be negative. If your reaction is acidic, all of your intermediate species on carbon will typically be positive. That's a very simple way to decide what you're going to do in a mechanism. Am I going to draw carbocations, which are positive, or next semester am I going to draw carbanions, which are negative? If you understand pH, that's a very simple way to get into these things and helps you keep a track of what's going on. So this slide is showing you the difference. The E2, everything happened at once. The SN1, the leaving group broke off. In the E1, the leaving group breaks off. That gives you this guy. Tertiary carbocation stabilized by what, Haldeman? Which is? Oh, yeah. Donation of electron density for adjacent single bonds. The more the better, right? So then what we have to worry about is what's changing here. This can be very confusing. All of a sudden, in the SN1, we did this. We went after the carbocation. That gave us a substitution product. Now, all of a sudden, for some reason, that needs to be explained, this is behaving as a base now. It's changing its characteristic from a nucleophile to a base, and it's going after this beta hydrogen, eliminating again to give you the alkene. Which of those two steps is rate determining, the first step or the second step? First step, right? Slow or fast? Slow. What type of process is this, going from here to here? Proton transfer. Yes, it is, right? So fast or slow? Fast. So use those things to start predicting, certainly for those who are doing well in this. So when you do the rate experiments and you dump in more base, it doesn't change the rate of reaction. That tells you the base is not part of the rate determining step. Therefore, this is a unimolecular process, right? That's where the 1 comes from in E1. And we'll find now that E1 is very much comparable to SN1. If you understood the SN1, this is just a twist. It depends upon different conditions, and those different conditions give you this second possibility. And of course, it wouldn't be much fun if the E1 didn't compete with the SN1, which it will. All right? So we have to keep busy here. There's a typical example. There is a typical example. You should start to put this together with your lab assignments. I know in at least one of the labs, the questions at the end ask you, in this reaction you get a little bit of alkene. You get a lot of SN1 or SN2, but you also get a little bit of alkene. Where does that come from? It comes from here. Yeah, it comes from the competition between a nucleophile acting as a nucleophile or a base. So I'm looking here at a tertiary system. Why do you think I need tertiary or secondary systems here? Why won't primary systems work here? I need a carbocation. I need a decent carbocation. So you're looking at tertiary and secondary being okay at this. And what's happening is that under these conditions, we are now bringing in some actual detail about the lab. You're heating this up. You will find now that heat promotes eliminations. over substitution reactions. And it'll be fairly obvious why. If you understand entropy, then this makes some sense. If you think about what's left over after this, what have I not got on here which I need to have on here to make sense? What's missing from there that's in the starter material? Yeah? How many molecules do I start with over here and how many do I get over here? 1 and 2. Is that positive entropy or negative? That's positive, isn't it? That's a good system. How do you make that system in your favor? How do you make delta S more significant in delta G? Raise the temperature. This is where the Orion stuff comes in. This is where the online stuff comes in. Those little details now come into play. So if you want to make delta S more important in a reaction that's going from 1 to 2, right, and you want to make delta S more important, heat the thing up. That's technically why this needs to happen. There's a bit more to that maybe on Friday, but that's where we're going now. In terms of how fast things happen, this does mirror the idea with the SN1. In primary systems, they're not going to give you a carbocation typically. They'll do something else. So they're not going to be very fast at E1, just like they weren't fast at SN1. If you go to secondary, you've got more alkyl groups that can help with hyperconjugation, so your carbocation will be more achievable. And in tertiary, you can do this at room temperature. Next week in lab, I think you do the SN1. Oh, you're doing the SN1, right? You've just done the SN1. How did you actually run that reaction? Did you heat it up? Did you shout at it? Did you shine light on it? Did you dance in front of it? Some people do that. How did you run the reaction? What was the temperature? It's in the palm of your hand. Okay? It's in the palm of your hand. Don't shout at reactions. We've tried it. It doesn't work. There was enough energy in your hand to make that reaction go, that SN1 go. So that means a tertiary alkyl cation is achievable even at room temperature. So that's why this is much, much faster, right? That's going to be a tertiary cation, much more stabilized by hyperconjugation, and it mirrors the same thing we talked about for SN1. Getting confusing. I've told you in the past about those mechanism summaries that I have on my website. Go look at those today. Get those things on your phone, your tablet, your washing machine, whatever you watch the internet on, get those things there so you can look at them. They're a nice little description of each mechanism as we go through them. Instead of having all the detail there, it's just broken down to the key points. So there's the basic outcome. There's the idea here. Primary carbocations, we don't like them. Secondary are okay. Tertiary, much better. Same concepts from the SN1 reaction. So in terms of how fast things happen, it's very similar to what we've already done. Having said that, these reaction profiles now should start to make sense. I had a leaving group break off. I had a base come in. How many steps? 2. How many barriers? 2. Which one is the rate determining step? A or B? A. What happened in A? Leaving group broke off, as it did with the SN1. It's the same idea. So then we get to the carbocation, which is there. Obviously, a secondary carbocation isn't as good as a tertiary carbocation because Haldeman says so. And then something else happens. And it's that something else happening that is the confusing part. So far, looks an awful lot like the SN1. This slide, I think, is pivotal. This is something you should have an asterisk, a smiley face, whatever you use to denote something important. This is where it goes. The E1 depends upon the substrate. It also depends upon the conditions and whether you can get to a carbocation or not. In this case, tertiary, no problem. Get to the leaving group. But for about 3 weeks now, we've been saying that carbocations react with nucleophiles, and we get a product that's called substitution. All of a sudden, we are telling you that in some cases, that nucleophile isn't going to behave as a nucleophile, it's going to behave as a base, and do this instead. And in many examples, it will do both. By the end of this chapter, we'll see different pathways giving different products from different mechanisms. So if you're not happy with the individual mechanisms, this will be tricky. Both compete. That nucleophile is a base, and that base is a nucleophile. In this E1, they're typically not strong nucleophiles. They're typically not strong bases. But they do have lone pairs that can behave as one or the other. So here is one of my favorite slides. Not just because I made it myself, but because it really is the beginning of understanding what's going on. Not just in sort of theory here on a slide, but also in the lab. This is a typical setup for an E1 process. A tertiary alcohol reacting with a certain type of strong acid, heating it up, and getting a good, in fact a very good, yield of this material. Do we understand yield in lab? Have we had to do a yield calculation yet? Have you handed one in? No. Before you hand your experiment in, because you need all those points from lab, make sure you understand what yield is. It is not grams of product over grams of starter material. Why not? Jacob, you okay? Why is it not just grams of product over grams of starter material? They have different molecular weights. So what do you turn them into? Moles, right? You turn your stuff into moles, and then you can do moles of product over moles of starter material, multiply by 100, that's your percent yield. Be very careful when you do this and don't get it wrong, because it's a bad habit to get into. So I'm going to start describing this now in the technical way we do it in lab. You can put these materials together in the reaction flask, you can heat them up for a while, and ultimately you get a very high yield of the alkene product. There is a change here. What we did earlier is we used stuff like HBr. We cannot use HBr here. Even though it's a very powerful acid, just like sulfuric acid, it does not give you elimination, it gives you substitution. But if you swap that HBr or HCl or HI for H2SO4, or the one that you'll get to use in about 2 weeks, which is very dangerous, so be careful, H3PO4. These types of acids allow you to go someplace else. They allow for elimination to happen. And there's something very simple about this. There's something very simple about the differences that you'll see very quickly here. You get this instead. So mechanistically, if I were to do this, I have H+. And I just said something about if I'm in acidic pH, all my intermediates should be positive along the way. So we can check that as we go. First arrow, go grab your proton. Why is it good to get a proton here? Much better leaving group, right? Much better leaving group. Fast or slow? Proton transfer. After that, this dissociates, it breaks off. Fast or slow? Slow. Call it dissociation, but it's really just a leaving group breaking off. Now, we get to this point where we've seen this before. We've seen the tertiary carbocation before. Previously, Br minus, Cl minus, I minus came in, we had an SN1 reaction. We don't have those species now. Those were very good nucleophiles, right? They're very good nucleophiles. We do not have a very good nucleophile in this system. In fact, what we have left over, if we've used sulfuric acid, is this guy. Everybody should know this structure by now. Sulfuric acid is that. And my negative charge, because it's the conjugate base of where we started, my negative charge is here. Do you think that's a stable species or an unstable species? Stable. Any ideas why? Resonance. In recitation, we're dealing with big ideas. We did that on Monday, we'll do it again today. The big ideas here. Because all you have to do is pull out from those big ideas the ideas you need to solve the problem. If this is stabilized by resonance, it's not in a particular mood to go react with anything. Yeah? And if you think about what's left in here, what is sulfuric acid dissolved up in? What is a bottle of sulfuric acid? What does it mostly contain? It's got some sulfuric in it, and it's got some... What's it dissolved in? Water. Sorry, water. So what we're going to see very quickly here is that water is just this marvelous, multi-purpose, useful material that can deliver protons, it can take protons, it can be a nucleophile, it can be a leaving group. It's superb, even in organic chemistry beyond biochemistry. I would argue that water is a stronger base than this guy. And we have a lot of it because it's a solvent. So what will happen in this last step is that this goes after this and takes this off. And that's where the alkene comes from. Is that a fast or slow? Fast. It's a deprotonation, proton transfer. Well, all of a sudden, we got a diversion. If you have a good nucleophile, that goes after the cation, you get an alkyl halide product. That was the SN1 reaction. Now we don't have a strong nucleophile, and we have to be careful how we set this thing up. The water can behave as a nucleophile or a base, and it will give you this elimination. So let's think about where I need to be. I'm going to do this now. I'm going to talk about it again on Friday, and I'll be out of this chapter on Friday. Technically, when you mix these things together, there's a lot going on. You have a tertiary alcohol, now all of a sudden it's giving an alkene, and it's giving H2O. This reaction is reversible. This reaction goes backwards. In chapter 9, we start on the right-hand side and we go left. Okay? We start with the alkene and we go left. That suggests that this is reversible. So I've got to worry about these ideas now. If I go from the alcohol to the protonated alcohol, why is that reversible? What do you think the pK of this guy is? It's a positive oxygen with 3 things attached. What does that remind you of? Hydronium, which pK is what? Negative 1.7. Is that a strong acid or a weak acid? Strong. So that should be able to give its proton back up. Where would the proton go? Water, the solvent. So yes, this is absolutely reversible in that first step. Then we have to worry about this, breaking apart. Yes, it's reversible. Once we get here, where do you think that molecule of water is immediately as soon as you get that carbocation? It's right next to that carbocation. Think about the transition state. It just snapped, it's still there. What does that carbocation need? What's this water got? Boom, they can stick back together. You'll be making that decision. Yes, Samtagantas, you will be making this decision. Yes? As zombies, living people, whatever, you will be making this decision. Okay? It's right there, it can reattach. If it reattaches, where does it go? It goes back over here. Well, that's not much use in terms of getting me to a product, but it is possible and it does happen. That water, sitting right there, can either attach as a nucleophile because it's got lone pairs, or it can be a base because it's got lone pairs. So the chance of this happening is real. The chance of this elimination thing is happening because to get to a stable product, I just have to take off that proton. If I do so, I will make this. Fair enough? All I've said so far is that those things are possible. Either it sticks back on as a nucleophile and goes backwards, or it takes off a proton and it goes in another direction. Well, in chapter 9, we'll explain why this is reversible too. Because alkenes react with acids. Not quite there yet. You get through 8, 9 is fun. Last thing I'll say. I've got 5 minutes. No, not the last thing I'll say. This is my last slide, but I'm going to talk about it. Go on. You get water and you get H+. That's the last thing I'm going to mention today. Okay? You get H+ as well. Deep breath. 5 minutes of this, right? Which do you think is more stable? Carbon with all single bonds or carbon with a pi bond? Carbon with all single bonds. So you'd expect this alcohol to be more stable. And if this truly is a reversible reaction, which do you think is favored, the alcohol or the alkene? The alcohol. How do you make this work? How you make this work is consider Le Chatelier's principle. If you think about the alkene, if I were to get rid of this alkene as I produce it, what will happen to the system? It will have to compensate, right? More of the alcohol will have to get converted to the alkene. And if I take that alkene out, more of that alcohol keeps coming through. How do you take an alkene out? Well, it's a fairly simple process. What do you think the boiling points are, the relative boiling points of that alkene? Do you think the alkene is higher or do you think the alcohol is higher? Alcohol is higher. Why? What can it do that the alkene can't do? Hydrogen bond. There is much more glue holding these things together. That will have a higher boiling point. So if I distill this stuff, which you've done several times now, if I have a reaction flask which contains alcohol, acid, alkene, and if I heat this thing up, which one boils first? The alkene, for the reasons just mentioned. So you'll do this in next week, maybe 2 weeks. You'll set the reaction up, let it bubble for a while, and you'll start distilling. As the alkene forms, you have the temperature right at its boiling point, and the alkene boils away. And that's irreversible. Once that alkene comes across your distillation apparatus and ends up down here, it's gone. So in the reaction flask, Le Chatelier's principle says that that must be compensated for, so more alcohol becomes alkene. Now think about distillation. What do you have to do to the flask to do a distillation? Heat it up. Does heat favor this elimination or does it not? Yes, because it's entropically favored. So that T delta S idea is not just in the sort of physical or chemical explanation for why this happens and how it works. It's also fundamentally an idea in the lab. You need to distill this stuff off. That's why it will work. Well, very last thing, I promise. The very last thing I will say today. And then Friday. Oh, it's Friday. And it's almost Halloween, so let's scare you. What did I consume in the first step of this reaction? What did I use? What was necessary to get the first reaction going? H+. What do I get back in this last step? H+. That H+ makes it go faster. What's H+? It's a catalyst. So when you do this, how much H+ do you need? Not very much. You don't need a full equivalent because you get it back at the end. So we are consuming acid here. It makes the reaction go faster because it's going to make a better leaving group, and then you get it back at the end. You've got a lot of work to do, so please go and do it.